Hello, welcome to lecture 3. Lecture 3 is about flow statics and buoyancy and stability. What we covered in this lecture is to calculate forces exerted on a fluid at rest on different type of surface, and also analyze the stability of floating and submerged body. So consider that in terms of the application, this is important when we build a dam, when we design, let's say, a window for a submarine, or even when we design a container. We want to know in terms of if they are subject to liquid, then we want to estimate the forces exerted on the side wall or on the wall dam, or yeah, this is also an apparatus that you are going to use in the lab and do some experiment, work out the hydrostatic forces when this surface is fully submerged and when it is half full. That's what you're going to do. So what is important in these hydrostatic forces is what are the resultant forces and what is the direction of this force, and also the center of resultant forces or center of pressure is important. So when we have a submerged surface and the surface is horizontal plane like this, we know that the hydrostatic forces or force at any point along this surface is estimated as rho gh, which h is the height of this one, g is gravity, and rho is the density of the liquid inside this container. Sometimes we add the atmospheric pressure to that one, then it will be basically the atmospheric pressure which is included in the calculation. But if we go based on the gauge pressure, we don't need to worry about that. So the resultant forces is estimated based on P plus rho gh. P0 is atmospheric, rho gh due to liquid, and the surface area of the force is acting. Now, where these where these forces act, this force is act at the centroid of the surface that this force is exerted. And centroid, you already know how to work out the centroid for different surfaces. Now, when we have like a vertical wall, obviously, then we know that in terms of distribution of hydrostatic forces, we know the gauge pressure at the surface would be 0, so the force would be 0, hydrostatic force would be 0, and linearly continue to the bottom of the tank. So if the height of this one is h, then this vector size would be rho gh, that means the pressure. However, suppose that you want to estimate the pressure on a window that you designing on the wall of this tank. So you can see at the upper edge of this, the pressure is rho gh, that means this side, and at the bottom side is basically rho gh of that one. Now this is how the pressure, but linearly change, and then obviously what we are after, the resultant forces. So to work out the resultant forces for these surfaces, we need to know the centroid of this surface. Say, for example, if the centroid of this surface is rectangular or a square, we know what the centroid is. If it is this surface gauge is circular, we know. Sometimes if it is a triangle, then we can work out what the centroid is. But obviously we need to make sure that this centroid is depending on the surface on we are assessing whether it is triangle or whether it is other form of surface. Now, to work out the resultant forces, the centroid, the distance from the vertical distance from the surface to the centroid of this surface is important. So this is one of the parameters. Then later on, what we need to estimate is where this force is acting. Now, looking at this figure, suppose that this is a window, which is this is a window. Let's say it is rectangular. We know the centroid of that in the plan, in the view that we have, is halfway through the centroid if it is rectangular or a square. So the central pressure would be below that one. Always the central pressure would be below the centroid of the surface. What we show in normally the centroid of the surface, we have, let's say, halfway here, this would be YC and this would be YP. So YP showing the central pressure, however YC showing the centroid of the surface. So to work out what would be this YC, as you can see here, this YC is that one. So YC is S, which is this one, plus half of this distance, which is B2. So this is YC. Now we can conclude that for any vertical surface that we want to estimate the hydrostatic forces on it, we need to have, if we know the centroid of the surface, YC, then this would be the pressure multiplied by the surface area. It gives you the force on that surface, which is in this case. If we consider atmospheric pressure, if we don't consider, then this will go. If we consider it, then it will obviously included in our calculation. Sometimes I said that this is the vertical distance, and this is very important. Most of the if we working in an inclined surface, let's say window is that one, then YC we will see on the later on the slide. YC would be that one. However, we consider vertical distance. Then on that case, we use HC. Remember, always to working the forces on vertical surface or inclined surface, rho GHC is important. Now, if it is the surface is vertical, then HC and YC are same. HC and YC are the same. If not, then we need to work out what the let's say this is the angle theta, so HC would be YC cos theta. That's all. So this is how it is considered. Now let's see the inclined surface. As I said, see the origin. Let's say you have a surface as is shown in here. Then you have surface plan view looks like that one, side view looks like that one. So we have two different terms. First is where is YC from this point, which is distance from the origin to the centroid of the surface. What is the vertical distance? Then vertical distance would be that one, which we say it is HC. So in that case, HC would be YC cos theta. Yeah? Now this is how. YP again would be, can be from, now you see this is YC, and YP would be this distance, which is showing here. That means now doesn't matter, we don't define HP or similar to YC. For YP is basically from where the origin is. So now what you see from this figure, and this is important for you to understand, okay, what we see here in this figure is that look at the term. Look at the term. This is the origin. This is Y. This is Z. Z is normal to the pages. Yeah. Now for now we don't worry about Z, but only we looking along Y direction. So centroid of the surface YC, center of the pressure YP, vertical distance from the centroid of the surface to the water surface is HC. Now, okay, the pressure, let's say now you consider a small element and you want to investigate the pressure. So you see that for this small element, P is atmospheric pressure if we include in our calculation, plus rho GH. Rho GH, basically H would be this distance. Let's say this is the element that we are talking about, and then this is H. So equal to P0 plus rho GYC sine theta. As you can see, this sorry, I said cos theta, but it is sine theta because I am talking about vertical, not horizontal. That's why. Okay, now you can see pressure on these elements would be P0 plus PHC. Now, if we want to estimate the resultant forces, we need to integrate for the holes over the surface and work out what the pressure is. Once we do that one, then FR become PC, that means the pressure that acting on the centroid. What is the pressure acting on the centroid? Is basically this one, rho GHC, PC or rho HC, which is in this term times area. So we can say for vertical and inclined surface that is the what is important is HC, that means vertical distance from the liquid surface to the centroid of surface that we are investigating. Then this gives us the resultant forces. So now for inclined and vertical surface, we can simply work the resultant forces in that way. And centroid, obviously you already have learned from statics, but what we can do, what we provide you as a formula sheet on your test or on your end of semester exam is this information that you may need for different shape, and you can work out what the moment of inertia is or what the centroid of those area is. Simply help you to that one, but obviously we don't expect you to do the integration, but you need to know how to use this information. So okay, the other question that raised, now we want to know what the line of action for this resultant force is. For the line of action, we say, okay, YP, which we obviously we want to know, we don't know what is that, times resultant forces that we already know that, we learn how to estimate, equal to integration of moment of individual elements around the centroid. So in that case, we can see that this equation, for the pressure, we could write it in this form if the surface is inclined. Then P0 is constant coming out of the integration, and we separate the integration, which would be YdA. Yeah, it would be YdA. Then plus the second part, which is rho G sine theta coming out of integration, and then Y stay in there, which would be basically this term. What is this term? This is moment of inertia along x axis. That means normal to the that means if this is y-axis, this moment of inertia around x axis. What is this is the centroid of the surface, which is, if you look at it from this equation, a times by c is equal to that one. That's why we say this term is yca, and this term is moment of inertia around the point that we take moment, not centroid, but around the point that we take moment. So if we take around any moment, now we need to transfer this moment to centroid. So we need, you already know transfer of axis is moment of inertia around centroid plus yc square a. This is how in mathematics we do the axis transfer. So yp is equal to yc plus ixxc. If we put it in this equation based on what we define, then equation can be written as this form. Yp would be yc, moment of inertia around the centroid, yc plus p0, which is atmospheric pressure, divided by rho g sine theta a. So this term, sometimes if we ignore atmospheric pressure, this term would be 0, and the equation can be simplified in this form. Remember, that's the equation which we can use to work out what yp is based on what we explained so far up to here. So what we have considered is that one thing I just want to refer here. Okay, one thing we consider, if this is the surface of liquid and this was the origin and the surface was like along here, we consider everything in this angle. But how about normal to the page? Yeah, normal to the page, if we saying that way, let's say this would be x or z or whatever we want to call. Let's say we say x. So this shape, which would be, if we expanded, it would be let's say it's a square a rectangular page. We consider along here, that means which is related to that one. So we work out what the yp is. But if how about xp? Because if we're saying in this direction, basically y, this one is y and this one is x. Yeah, this one is x direction. So in the x direction, then we will have a yp, xp as well. So that means this point, which is this center of pressure, will have two coordinates. One would be x, one would be y. But most cases we can ignore, assume xp is 0. Why? Let's say, for example, you have a rectangular surface. Then if you choose the axis of symmetry along y, which this was O, yeah, if we choose that one, then xp would be 0 because this is the point we have selected. However, if we have a circle, then xp would be 0. If we have a rectangle, a square, again would be 0 because everything with that. However, if we have a triangle which is does not have axis of, this one has got axis of symmetry, again xp would be 0 because that side and that side would be the same. However, we might have a triangle like, let's say, this one, yeah, which does not have any axis of symmetry. Then in that case we need to consider what xp would be. That's the O, what xp would be. So for this, if any figure has axis of symmetry, yeah, we can simply assume y direction is along axis of symmetry, and then we can assume xp is 0. However, if the shape does not have axis of symmetry, we can use this equation to work out xp as well. However, this time we need to know what the xc is, and equation would be this form. Then moment of inertia would be xy direction, but most of the cases we have axis of symmetry. Just in case we don't have, then we consider xp. So in answering a question, going back to you know what we if you have been asked a question that okay, find a coordinate for center of pressure, you can say I have chosen axis of symmetry. If the shape has done, then xp is 0. However, yp estimated from this equation. But these are the things that when you're answering the question, you need to clearly answer the question. This figure we explained that if you need moment of inertia, then you can work out from there. Then this is a question that helping us to answer what we have learned. We can use this principle and answer the question. Now, a 6 meter high and 5 meter wide rectangular plate, which is basically 6 meter is from here to there, and normal to the page is 5 meter. Block the end of a 5 meter deep freshwater channel. That means this one, basically 5 meter, is blocking that one, and we have something here which is holding the gate. As per the figure is shown, the plate is hinged about a horizontal axis along its upper edge, which is this point, and is restrained from opening by a fixed ridge at the end, which is point B. Determine the force exerted on the plate by the ridge. That means we want to see what force is exerted to the ridge. So first we need to work out what the hydrostatic pressure force are, which is in this case has been shown. Then for working out the hydrostatic pressure, we need to know what the centroid of this plate is, which is obviously rectangular, and we know. Then we can easily work out what HC is, which would be half of that. Remember, from where the centroid would be from where the surface of the liquid is, not centroid of the whole surface, because partially submerged in water. And in here we have included also atmospheric pressure. So this term is conversion to kilonewton, but the rest is rho, which is 1000 kilogram. G is sorry, we didn't consider atmospheric pressure. G is acceleration of gravity, and hc is 5 divided by 2. Then it would be total force would be pressure would be that one. So if we multiply this pressure by the surface area, it is the force that it is exerted on the surface. Now we need to work out what the line of action for this plate is, and the equation that we used is we said yp is yc plus moment of inertia xx yca. So if you put yc in there, which is 5 divided by 2, 2.5 here, so 2.5 here, 2.5 here, 5 by 5 here, and then moment of inertia you need to work out, and then it gives you what would be. This is one way from formula, which hasn't been used in this equation, but what has been in this used in this equation, in this question, is that if we can also work out from pressure prism. What is the pressure prism? Pressure prism is, imagine this is the distribution of pressure which extend to that side as well. Yeah, extend to that side as well, and then you can see that means the pressure is like a cube in here, which if you work out the centroid of that triangle, then it gives you where the force is acting, because this triangle showing the distribution of pressure. So the distribution of pressure. So the centroid of this triangle is where the force is acting. If this is H, then from here to the centroid of this triangle is 2/3 of H. Yeah. So that's why you see YP here is considered as the centroid of this prism. So we want to say, if you can plot the centroid of prism, then obviously we can have simply work out what the centroid of this prism is, and then from there we can simply work out the center of pressure. However, if this is difficult for us to plot, then we can go based on the formula. My suggestion is that you just go and work out YP from the formula as well, and to see what the answer you're getting. You should get same answer. So now up to here we know the center of pressure. Then if we want to work out the forces where they are acting, we have one force which is hydrostatic forces, and this is the reaction force we have. So if we take moment of inertia around this point, which is, then we can say Fr times S, which is this one, and where it is acting, Yp, yeah, equal to reaction of this ridge. So reaction of this ridge times its distance around this center. So the only unknown in here would be F ridge, which would be how much? 443 kilo Newton, and simply we answer the question. Okay, we talk about pressures prism, and I am sure now you understand. So there are two ways of finding the center of pressure. One is if we are able to plot the pressure prism, then the centroid of the pressure prism would be where the line of action for resultant force would be. If we cannot work based on the pressure prism, then we can simply use formula that we have introduced. But pressure prism is a virtual distribution of pressure on the surface that we are investigating. Sometimes it is easy to work out, sometimes it is difficult. Then we need to go based on the formula. So this is what is showing is a submerged rectangular surface, and it teaching us how to work out Yp, which is again Yc plus moment of inertia, and then this is if we include atmospheric pressure. But if we don't include atmospheric, this would be 0, and exactly with Yca, the formula that we already introduced, which is this one, and Xp, if there is no axis of symmetry, then we need to work out what the Xp is. So in this case, you can see that we can use obviously the parameter, the definition for each parameter is given in this figure, and write in this formula. I don't want you to memorize the formula, but it is mainly important you learn this, how to work out with these things. Other than that, you don't need to worry about all memorizing. This is not, never ever go base just, oh, that formula for this case, another formula for another case. You need to learn fundamental and then apply the fundamental without occupying your brain too much. So you can see for a tilted rectangle plate, PCA, which we already know how PC is rho GHC, which is this is what is saying here. But if S this touch to the surface, then S would be 0. You're putting S0 in here. The equation will be simplified in here. Basically, this is special case derivation of another formula which you don't need it, but it is important to understand how these are working. Okay, vertical force we already said, I think we discussed. Horizontal surfaces we already discussed. Now you know whether including atmospheric pressure or not, then we can go based on that one. These are basically what we have already said for vertical and horizontal surface. Now we have hydrostatic forces on submerged surface, on curved surfaces, which is also important. The simplest things that you need to do when the surface is curved, it's better that you split the force into its components. Say, for example, fluid is in there, a force acting on here, then you need to split it to Fx and Fy, which is this direction, yeah? And then through that one you can work out what the F resultant is. Now, this is the simplest way and easiest way to do to work out on the curved surfaces. How we consider, there are a couple of considerations I want to explain to you, that how you go how you go for estimating horizontal forces. Let's say, for example, first things that you need to do if you plot a vertical line, and for the surface under investigation, you project this curve into this vertical line. So then for estimating the horizontal force, it is you need to assume that you are estimating the force on these surfaces. How we estimated, we already learned to work out this force, rho G H C A, yeah? But this time we work on projected surfaces. So for estimating, in brief, for estimating horizontal force on a curved surface, we need to project the curved surface on a vertical axis and then treat it as a vertical surface. In our calculation, we need to consider projected surface. That's what, for example, this curve, if it extends 2 meters on the normal to the page, then the surface, projected surface, would be a rectangle. HC would be for a rectangle. This is how we need to do. How about vertical forces? Vertical forces can be one. Okay, if you have a case like this, there are different ways of doing that. If I estimate the weight of water in there, then this weight would be vertical forces. Okay, where the line of action for the vertical force is, the line of action would be the centroid of this volume would be the line of action for vertical forces. What would be the line of action for horizontal force is exactly similar to what we said before. So we treat it this way, and if we want to know the angle, how the angle of that is, then we can simply do that one. Now, this is another case that I want the figure on the left hand side I want to explain, and this is also important. Again, for horizontal forces, we just draw a line, yeah, draw a line, project this surface, which is curved surface, to this vertical line and treat it as a vertical plate, and then work what is where the centroid of this is from HC, and then area of this would be projected area. This is something that you need to consider, not the area of curved surface. So we can estimate the resultant forces based on Fr is rho GHC A projected. Yeah, this is how we do for the horizontal force. How we can do for vertical forces? Okay, vertical forces base, I said on the previous example, I said the weight of water above that surface would be vertical forces. Now imagine, can we do for this curved surface? You can see that on the right hand side there is no liquid. Then what we should do, if we assume this plate is very thin, do you think if we assume water is in this side giving same pressure on the surface compared to when water is here? Yes, basically what we want to say that whether we assume water in this side or this side is same, doesn't matter, as long as we assume this plate is thin, which doesn't impact many things. So we can estimate the vertical force, but this vertical force, because we imaginary assume the water is on the right hand side, then the direction we need to pay attention. Direction should be upward. This is one way of simple estimation of vertical forces if you don't want to go through more complicated calculation, but providing that such a assumption can be made. Now the second approach, which is also explained in your textbooks, is that okay, we assume a force acting upward. Yeah, force acting upward. What that means? Meaning that Fy. How we estimate Fy? Similar to having a horizontal surface. That means from there to there, yeah, is Hc. Yeah, sorry, Hc. So for vertical forces we can say Fy is rho GHC times area of that one. Yeah. Now we assume from this end line or this horizontal line. Now the volume of the weight of water is in here, need to be deducted from that one. So Fy would be F vertical, I would call this one F vertical, would be Fy minus weight of water on this area that I just put dashed line. This is also a way of estimating, but you can see through this process you need to do a number of calculation, which obviously depend, but sometimes it is easy to assume fluid is on the other side and do it the calculation in the way I explained. Sometimes it's not, depend on how you feel convenient, is convenient for you to do the calculation. Similar things can be applied in here. Again, horizontal force is projection to this line, treat it as a vertical plate and work out. For vertical forces we can draw a line like this, then we have Fy upward, weight of this part W1 and weight of this one W2. So vertical force would be Fy minus, because it is downward, W1 minus W2. This is easy. We can W2 maybe is easy to work, W1 also easy to work, which is weight of water there, and Fy is also easy to work. This is how we treat curved surfaces. If we have a multi-layer of fluids, obviously we need to, when we want to estimate the vertical force in a plate, in this case, for example, for oil, we need to estimate force due to oil and also force due to the lower part, which is Fr2, another water, and then the sum of these two would be basically vertical forces acting on that one. This is an example which I want you based on what I explained for the curved surfaces. This is a cylindrical cylinder which we put it in there. Then we need to work out what the hydrostatic force are, let's say Fr, and in this case Fr would be Fx and Fy. So you just need to, based on what we explained, try to do yourself. Work out project to vertical line. It is horizontal would be projected line, which would be along this one. Vertical one would be we can, let's say, just put it vertical one would be let's say we do it like that. One Fy acting upward from here, then this weight acting downward. So vertical would be Fy minus weight of water in there. That's all. Now try to do it yourself and then see what you're getting. I leave this example which is from your textbook for you to do it. Many of you, some of your lecture has got an example from textbook, which sometimes I put it at the end of the lecture, sometimes between the lecture note, but obviously you can go yourself through. Some of it I may, if we have time, I may go through it. Otherwise, yes, this is, you need to do a bit of practice and you have already the answer. Okay, now we finish with the hydrostatic forces on plane, vertical, and inclined and curved surfaces. Now we want to work on learn about buoyancy and stability. We want to learn because stability is somehow related to buoyancy. What buoyancy means? Buoyancy means if you go, for example, in a pool, you feel your weight is lighter. Okay, by how much? By the weight of water that you have displaced. For example, we put a ball, a sphere, inside, push it down in the pool. If we remove our hand, it will jump up. Why this goes? Because buoyancy force push it up. How much this buoyancy force is depend on how much you have pushed the ball down. If it is halfway, then the weight of water which is displaced by the ball, which is its halfway, then this is the force acting upward. If you immerse the ball in the water, then the weight of water would be the whole volume of ball times density and gravity of times density of water. Then you can see the more goes on the water, the ball, then the more a buoyancy force would be. So it is buoyancy force is an upward force fluid exerted on a body immersed in it. The buoyant force is caused by increase of pressure with depth, basically. That's the buoyancy force, which is normally shown by this one. Density of the fluid that it is displaced times gravity times volume of the object which is immersed inside liquid. So what Archimedes' principle says, the buoyant force acting on a body immersed in a fluid is equal to the weight of the fluid displaced by body, and it acts upward through the centroid of the displaced volume. So what does it say in this last part? So if someone asks you what is the line of action for the buoyancy force, you should say it is the centroid of displaced water. Whatever the shape of object is, then displaced water, that volume, basically volume of displaced water is the centroid of that one, is the line of action for buoyant forces. That's how it is. Now, normally, the buoyant force acting on a solid body submerged in a fluid and on a fluid body of the same shape at the same depth are identical. So that means if I put a piece of metal and also put a piece of wood in water, immersed in water, the buoyancy force is same, no difference, no matter what the mass of these two objects is. That's what it says. It is also said the buoyant force acts upwards through the centroid of the displaced volume. So displaced volume looked at that one. Centroid of that is here, then the centroid of buoyancy force would be that one. And also for a solid of uniform density, its weight also acts through the centroid. So if the object is metal from one material, is not different material, then the centroid of weight, center of weight and center of buoyancy force are the same, similar to that one. However, if the part of object is made from different material, even the buoyancy is the same, but the center of weight may not be the same because the material is not uniform. Now, if we have for a floating body, basically density of, if an object, we throw an object in a water or liquid, if its density is less than density of a fluid, it will come to the surface and it will be float. If the density of the object and density of liquid is same, is suspended in the water. However, if density of the object is greater than density of the fluid, object will be sinked. For these two, buoyancy is same. However, for this one is less because only this portion is submerged. Now, about stability of immersed and floating body. Immersed means under water, floating on the surface. Now, you can see a vessel or ship, a cargo, is normally float in the water. Now, it is important for us to understand what means by stability. Now, imagine a ball sitting on this curve. If you move the ball to this side or this side and release it, it will be back to its original position. Then we say this object is stable. Now, let's say due to wave, this cargo turn left or right. If cargo just turn left or turn right up to certain angle, but again come back to its original position, we say this cargo is stable. However, some objects are neutrally stable. What that means, if you move this ball to this side or this side, it will stay at the position it is. On a stable position, on a stable situation is that, so if the curve is reverse, then if you move ball here or move ball here, it won't come back to its original position. So same for that one. So if the vessel is tilted to the right and doesn't come back to original position, we say it is unstable. That's the concept of stable and unstable for a floating body. Now, sometimes the stability of immersed body is different. Now, looking at if you have an immersed body, then for that immersed body you have a center of gravity and a center of buoyancy. If the center of buoyancy, if the object is immersed in liquid, so it's different from floating. So if the center of buoyancy is above the center of gravity, we say the object is stable. Why? Because if you tilt it this way or tilt it that way, it will go back to its original position. However, if the center of buoyancy and center of gravity coincide, then we say it is neutrally stable. That means no turning moment is created. However, if the center of gravity is above the center of buoyancy and the object is immersed, then if you're tilted to this way, you can see the moment that acting is in the direction that it is tilted. Then in that case we say the object is unstable. So this is what the stability for immersed body means. The text is written in here, obviously explain what we have discussed so far, and you can read it yourself. If there is any question, come and ask, please. Now, one item that is defined for stability of floating body is metacentric height, because this metacentric height, it is very important parameter to estimate. Now, let's say, for example, we have a vessel here, and then there is a line passing through center of buoyancy and center of gravity. Now, if it tilted to the right, as you can see here, then the center of gravity, the line passing through the center of gravity would be this one. The line passing through the center of gravity would be that one. Yeah. Now, sorry, the center of buoyancy would be that one. So these two lines intersect at a point. This point is creating like a pendulate situation. Then that vessel can swing around it. Then this is called center of metacentric height. The higher this metacentric height is, very high, then the more stable a vessel would be. So there are situations that if the center of metacentric height, similar to that one, fall between the center of gravity and center of buoyancy, then in that case the object become unstable. Why? Because if you're turning the vessel in this way, you can see the turning moment also acting on this way, then the object is unstable, because turning moment and turning of the vessel is the same way. However, for this one, when you're turning the vessel in here, a turning moment acting on the other way. You see the turning moment acting this one due to this anti-clockwise, which is obviously due to this center of buoyancy and metacentric height. So this is how important a metacentric height is. So it is the distance between the center of gravity and metacenter, the intersection of point of line of action of buoyant force through the body before and after rotation. This is what the metacentering. I explain it in a try to explain it in a simpler way, and I hope that this would be more understandable to you in terms of how the metacentric height is interpreted. So in summary, what we have learned in this lecture was pressure force on submerged, plane and curve and inclined, vertical and so on. We learn a bit about pressure prism. We learn about Archimedes principle and buoyant force and stability of immersed and floating body. I hope that you enjoyed this lecture. Please get in touch if you have any question. Thank you and have a great time.